Okay, so today I'm going to be talking about the possible link between convection and African easterly waves, and specifically a mechanism through which they interact. And so my name is James Russell, and first of all I'm going to give an introduction on African easterly waves. So they are synoptic scale disturbances that cross the Sahel region of Africa during the West African monsoon period, and they have a period of around 3 to 5 days and a wavelength of around a couple thousand to a few thousand kilometers. And they are important because they lead to a majority of tropical cyclones in the Atlantic basin, and also some in the Pacific, and also because they modulate rainfall in the Sahel, which is a highly populated region, which is this region of Africa, and also in the ITCZ across the Atlantic and the Sahel. And so since the 60s and 70s, it's been thought that African easterly waves were simply just instabilities on the African easterly jet, which arises as a result of the temperature gradient between the Sahara and the much cooler Gulf of Guinea. But in 2006, Hall, Clardes and Thorncroft, in what is now a very important paper on easterly waves, showed that instabilities on the African easterly jet are too weak to sustain the observed easterly waves that we see. Or in other words, what they did was a number of idealized simulations that showed that simple damping on those instabilities was enough to remove them entirely. And so, as a result, they concluded that easterly waves needed some other energy source or some other growth mechanism through which they can keep going. And so, for a long time, people have associated convection with African easterly waves. And since 2006, many have proposed that convection is this alternate energy source. However, no one's proposed an exact mechanism through which they interact and through which they can grow the wave. Convection can grow the wave. And so that's what this talk is going to be on. And specifically, the mechanism we're going to be looking at is the diabatic Rossby wave mechanism, or the DRW mechanism for short. And this is a growth mechanism typically observed in mid-latitude or some mid-latitude cyclones, and it occurs in that strong baroclinic zone associated with mid-latitude cyclones. And we actually have that strong baroclinicity in the West African monsoon region, associated with that temperature gradient between the Gulf of Guinea and the Sahara, and that's actually on the same order of magnitude as that in the mid-latitudes. And so this mechanism occurs when convection is forced ahead of a potential vorticity anomaly. And that convection then leads to diabatic heating, and that's shown in figure A in the schematic below, which is an adaptation from Parker and Thorpe 1995, which is now one of the seminal papers on diabatic Rossby waves. And so that diabatic heating then leads to vertical gradients in diabatic heating, and through potential vorticity theory, you can show that this leads to a generation of low-level potential vorticity, which you can now see in figure B of Barker and Thorpe. And it's ultimately this new potential vorticity that grows and propagates the wave westward, and this is in the westerly, or eastward in the westerlies. But we want to adapt this mechanism and use it in the easterlies for easterly waves. And so here I'm going to present our hypothesis. But first, I just want to present exactly how I expect the DRW mechanism to occur for African easterly waves. And so what we have here is a potential vorticity anomaly at 650 hectopascals, which is the approximate maximum in African easterly waves. And that PV anomaly leads to a balanced circulation, which you can see here, which then leads to northerlies ahead of the trough, which is this positive PV anomaly. And that then leads to isentropic lifting, vertical motion and convection as a result of that, and obviously diabatic heating as a result of the water vapor phase changes, or water phase changes. And then that diabatic heating through vertical gradients and diabatic heating leads to a new PV anomaly. And so this is exactly how we expect to occur, and we expect the wave to grow and propagate through this mechanism westward. And so with that, our hypothesis is that the DIW mechanism, or the diabatic Rossby wave mechanism, plays a role in the growth and propagation of African easterly waves. And so our predictions are that this mechanism that I've just explained occurs. We're going to be looking for PV growth due to diabatic processes ahead of a previous PV anomaly, and in association with the northerlies in general of the wave. So we're going to test this using a WRF simulation. So this is a 3612 4-kilometer WRF simulation that you can see on the right here. And so this 4-kilometer WRF simulation has no convective parameterization, and this is the one we're going to be focusing on, this domain out in this nested domain here. And so the wave we're going to be looking at is the pre-Hurricane Earl wave from 2010 that crossed this region during the 19th to 25th of August. And we're going to be using the parameterizations as below. I'm not going to go into detail on those, and we're going to be using ERA trim as the initial and boundary conditions. And so we have a control simulation with full physics, nothing changed. And then we also have 3 sensitivity studies with limited moisture. And the idea behind this limited moisture is that we are able to limit convection to certain extents. So basically what I did was I multiplied the soil moisture and the relative humidity in the era interim boundary conditions by 0.9, 0.7, and 0.5 for each of the cases, and as a result, what we get is a limited convection, more and more limited convection in each of them. And so, first of all, looking at our comparison with reality, these are longitude time plots of the meridionally average 650 hectopascal meridional winds, and also the rain rate and contours. So you can see on the right we have era, interim, and trim. This is our best estimation for our observations, and then we have our WRF control on the left. So you can see we have northerlies in the shades, led by the trough, which is this sort of white area in between, and then the ridge, the southerlies in the red. And so that's moving through time. And what we see here is that we have convection or precipitation in the northerlies that transitions into the trough once we hit the West African coast around this region here. And so that's what we see in the observations. We need to now question whether we see the same in our WRF control case. And so what you can see here is the northerlies led by, or the northerlies lead the southerlies, and we can see that we have convection in the northerlies that transitions into the trough around the same region it transitioned into the trough over here, right around the West African coast. And you can see that we have approximately the correct phase speed. These are the same arrows on both figures. So it moves through a domain at the same speed, roughly. We also have approximately the same intensity changes. So you can see at the beginning of the simulation here, we have an increase in the intensity of the wave, or of the southerlies here, and then a de-intensification later on, and a re-intensification as we cross the West African coast, although that re-intensification isn't quite as strong as the observations. But then we do see this strong intensification of the wave, where we actually saw a de-intensification of the wave between around 10 east and 0 degrees, or the Greenwich meridian. And so this may be associated with the convection in this region. You see there was this sort of MCS that moved through the trough for some parts, and that may be associated with a increased PV structure there, whereas we didn't see that so much in the observations, although it's hard to tell with the resolution. But overall, we have a generally similar simulation to our observations, and we're not trying to get it exactly right, we're just trying to show that this mechanism occurs. And so if we look now at Hofmoller's of the same thing, so this is our control, our 90%, our 70%, our 50% simulation, you can see that we have a weaker wave as we go down in moisture. So here's our control, strongest wave, then we have sort of some weaker meridional winds, and slowly they get weaker and weaker until we hit the 50% simulation. Now if you look at the precipitation, you can see here that we have strong precipitation, slightly weaker precipitation, not as widespread, especially at the start and especially toward the end of the simulation. And then in the 70%, that precipitation is nearly all but gone. We do have something running through the northerlies here, and then a little bit toward the end, but that wave seems to have disappeared almost once we get to that time. And then in the 50%, there's no convection or precipitation that follows the wave at all, but we do get a little bit toward the end. And so you can see here that we've got an association between less convection or less moisture and a stronger or weaker African easterly wave. And so we have an association, but we need to show that we have causation as well. And so I'm going to do that using a potential vorticity budget. And this PV budget is a PV budget on pressure surfaces from Zhang and Ling 2012. This equation shows you the PV tendency. So that's your local potential vorticity growth or decay with time. And then we also have, on the right-hand side, adiabatic PV sources contributing to that overall PV tendency. And you can see from the form of the equation here that it's mainly advective. And then we have diabatic PV sources. And you can see from the form of the equation here that this is as a result of vertical gradients in diabatic heating, which is what we're going to be looking for. And so what we're going to be looking for is these diabatic sources that are stronger than these adiabatic sources. And we're also going to be looking for the diabatic sources to be leading the overall PV anomaly, so ahead or west of the overall PV anomaly. And so now I'm going to show you an animation of longitude time plots of PV in both. So these are the contours of potential vorticity. You can see the PV anomaly associated with a wave moving through in both figures here. These are the same simulation, the Whorf control case, but just and both same contours. And on the right we have the diabatic PV sources, and on the left we have the adiabatic PV sources shaded. So what you can see here, so this big blue blob that came up from the surface, that's associated with the diurnal cycle, so that's not associated with the easterly wave. So now we've started the simulation again here. So this is a PV anomaly from the wave entering the domain, and you can see we have diabatic sources leading the positive diabatic thing, or the positive PV anomaly, and then the PV anomaly tends to weaken when we see a weakened diabatic sources. Especially around now, you can see it really weakening. Now there's no diabatic sources, actually they're negative in some cases. And then we get a re-intensification of the convection and more diabatic sources back over the West African highlands and the Guinea highlands and the West African coast, where convection is prominent in that region. Now if we look at the adiabatic PV sources, you can see that they are positive and they are strong, but they tend to be weaker than the diabatic sources. And in some cases, if you look, especially in the lower levels, you can see that they're actually negative of the diabatic sources. And so the adiabatic sources are not likely to be the main result of the growth of the wave in that case, and especially the deepening of the wave. You can see we had that deep PV structure that gave us and that seemed to be mostly from the diabatic PV sources. And so first of all, I just now want to show you those in kind of snapshots. Easier to show this in a snapshot rather than just the full animation. So here we have the same diabatic sources PV anomaly at hour 30, and you can see we have positive diabatic PV that leads our potential vorticity anomaly. So this is west of the maximum in PV at the sort of upper to mid levels. And then we also see, this is a really important result from this study, is that the diabatic heat source, or the diabatic PV source, tends to lower the maximum PV anomaly and deepens that PV anomaly. So this PV structure here is what we get from this result here. And that has implications for hurricane genesis, and I'll talk a little bit more about that in the summary. But then if we move on to hour 78, here you can see that the PV anomaly is weakened. This is now a 0.1 PVU maximum contour, whereas before we had a 0.2 PVU maximum contour. And here we see next to no diabatic sources. There's some weak ones here, but there's next to nothing in general. And it seems that the diabatic PV generation dying off has ended up leaving the wave to just be weakened. And then if we look at hour 102, we have a re-intensification over the West African coast and the Guinea Highlands. So this is a region conducive for convection. And so that PV anomaly starts to grow again at this point, and it's actually growing again at a lower level. So maybe also more implications for hurricane genesis there. So now I'm going to look at our sensitivity study. So this is an animation of the same figures as we saw in the last animation. And so what you can see here is our PV anomaly from the easterly wave entering. You can see it's weaker for the most part over there. And it's also based higher. There's none of that deep PV anomaly that we saw associated with the previous wave in the 100% case. You've got this strong diabatic, strong advective. You have an advective growth growing the wave aloft. There's no diabatic source deepening that wave. And so I'm just going to let it roll through again and come back to the start. So hour 144. Okay, so now we see, here we are, PV anomaly coming through again. There's no deep structure here. We haven't got anything in the lower levels, and the adiabatic sources tend to grow that very clearly and lead that PV anomaly. And as you can see, still no diabatic sources. Adiabatic sources growing between 4 and 500. There's no wave in these lower levels, which we see in the observations. And so here this really gives us some strong backing that the diabatic PV source is what grows the wave at the jet and the lower levels, whereas the adiabatic PV source really tends to just grow the wave aloft. And so in summary, we have shown that less moisture is associated with a weaker easterly wave. We've also shown that diabatic Rossby waves, or the diabatic Rossby wave mechanism, appears to be growing the easterly wave. And we showed this by looking at our control simulation. So we saw that in that control simulation that the diabatic PV source tends to be greater than the adiabatic PV source, or of the positive sign, whereas the adiabatic PV source was the negative sign. Also, the diabatic source led the easterly wave PV anomaly. And then we also saw that diabatic sources tend to preclude the easterly wave intensity changes. And these were all things we predicted would occur as a result of the DIW mechanism occurring in easterly waves. And then one really important result that I noted was that the diabatic source tends to deepen the easterly wave PV anomaly. And this really has implications for hurricane genesis, where you need to grow a small potential vorticity anomaly at the surface in order to get a surface circulation that will end up resulting in a hurricane or a tropical cyclone. And so we've shown here And so we showed in the sensitivity studies that we don't get that without the moisture and the convectives and the diabatic sources of potential vorticity. And so really what it says is that diabatic growth of potential vorticity at the low levels is key for hurricane genesis from easterly waves. And so in future work, I would like to examine other easterly waves. Obviously, this is just one easterly wave, and this case may not be representative of the full spectrum of African easterly waves. And so that's an important thing that we need to do. And with that, I'm going to end my talk here.